All right, today we're going deep. We're diving right inside a single CPU core to tackle a question that sounds, well, impossible. How does one tiny little processor manage to juggle dozens, sometimes hundreds of programs all at the same time? I mean, it's a total paradox, right? A single CPU core, at its heart, has a one-track mind. It can only execute one instruction at any single tick of its clock. And yet, right now you've got your browser running, you're playing music, your email's checking for updates, and that's not even counting all the background stuff. How? That's the magic trick we're going to pull apart today. Okay, so to get our heads around this, let's picture the scene. We're zooming way in on a single ARM core, the kind that powers your smartphone. It's just chillin', running a normal program. We'll call it Process A. This is all happening in a pretty restricted, low-privilege area called userland. Everything's calm, everything's normal, but that is all about to change.
And then, bam, something happens that the CPU absolutely positively cannot ignore. Now, this isn't a bug or an error, it's a completely planned signal, and it's totally fundamental to how modern computers work. It's called an interrupt, and it's about to kick off one heck of a chain reaction.
So in our scenario, a simple hardware timer decides, hey, time's up. It sends a little electrical zap through a component called the Generic Interrupt Controller, or GIC for short. And that GIC then flips a switch on our core's interrupt request line, the IRQ line. You can literally think of it as someone ringing the CPU's doorbell. And trust me, it has to go and answer it. And this, right here, is where things get really cool. Before a single line of software, before the operating system even knows what's going on, the CPU's own physical hardware circuitry just reacts. It's an automatic, hardwired, lightning-fast response. Instantly, the hardware does three critical things. First, it saves the program's current status, stuff like whether the last calculation was 0. Second, it saves its place. It's like slamming a bookmark in a book so it knows exactly which word to come back to. And third, it flips its own switch, moving from the low-power user mode to the all-powerful kernel mode, and it immediately jumps to a prearranged spot in the operating system's code, ready to handle what just happened.
And this shows you this really smart division of labor that's going on. The hardware is lazy, in a good way. It does the absolute bare minimum required to not get lost. It saves the bookmark and the status flags, and that's it. The rest of the program's workspace, all its notes and scratch pads, are still sitting there. Saving all of that stuff, that's software's job.
And just like that, we've jumped the fence. The hardware's reflexive, instant reaction is over. Now the Linux kernel is in the driver's seat, running with full privileges. And its very first job is to carefully pack up the entire disk of that user program that just got interrupted.
So how does Linux do this? Well, it uses this special custom-made container called a pit regs structure. Honestly, the best way to picture it is like a perfectly organized box. It has a specific labeled compartment for absolutely everything that user program was working with. Every single register, its stack pointer, and yeah, even the bookmark and status that the hardware saved for it a moment ago. So now, the operating system starts packing. It meticulously goes through and saves all 30 or so of the user program's working registers, one by one, into that PT-regs box. It also tucks away the bookmark and status from the hardware. At this point, the complete state of Process A is safely packed away, frozen in time on the kernel's own shelf, called the kernel stack.
Okay, so Process A is safely on ice. Now the kernel can finally ask the big question. What do we do now? And this, my friends, leads us to the main event, the performance we all came to see, the context switch.
Hey, remember how this whole thing started with a timer? Well, this is why. That timer is basically the scheduler's alarm clock going off. It's the operating system saying, okay, Process A, you've had your fair share of CPU time, your little time slice is up, time to give someone else a turn. So the scheduler quickly does its thing, it looks at all the waiting programs, and it picks a new one. Let's call it Process B. The kernel makes a note of where it stored Process A's box of stuff. And then comes the pivot, the most critical step. The kernel changes the CPU's stack pointer, which is like changing the address on a GPS. It tells the CPU, stop looking over here at A's stuff. From now on, look over there, where B's stuff is. Then it just unpacks Process B's registers and gets ready for the handoff. And that right there, that is the absolute heart of this entire magic trick. It's so elegant. With one single instruction, changing one single register, the stack pointer. The CPU's entire world, its entire context, has been swapped from Process A to Process B. It's an incredibly powerful and efficient sleight of hand.
So the very last step is this special instruction called ERET, which stands for exception return. It's basically the kernel yelling to the hardware, "All right, we're done in here, your turn." The hardware hears this and does the exact reverse of what it did at the beginning. It grabs the bookmark and status for process B, restores them, drops the power level back down to userland, and poof! Just like that, process B is up and running with absolutely no idea it was ever paused in the first place. Okay, so that's one core. Makes sense. But your phone, your laptop, they have lots of cores. How does this whole intricate dance possibly scale up?
Here's the most important thing you need to get. Think of each core as its own little island. When that timer interrupt hit our core 0, look what was happening on the other cores. Core 1 and Core 2 were completely oblivious. They just kept chugging along, running process C and process D without missing a single beat. The entire dance we just watched, the interrupt, the save, the switch, it all happened exclusively on Core 0's little island. But what happens if the scheduler on Core 0 realizes, hey, this super important task needs to run, and Core 1 is the best place for it? Well, it can't just reach over and take control. Instead, it sends a little message in a bottle called an interprocessor interrupt, or IPI, through that same GIC controller. Core 1 gets this message, and to it just looks like another doorbell ring. It kicks off its own completely independent exception handling process, and eventually its own scheduler wakes up to see what's going on. Okay, let's take a breath and walk through that entire journey one more time, from start to finish. Let's see the whole picture. So it all starts with process A, just running along in userland. The hardware interrupt hits, forcing a jump into kernel mode, and the hardware quickly saves the bare essentials. Then, the Linux kernel steps in and carefully saves the rest of the registers. The scheduler makes a decision, it's time for a change. The context switch happens with that one pivotal swap of the stack pointer. And finally, the ERET instruction tells the hardware to return us to userland, but this time running process B. It's a beautiful, perfectly choreographed dance.
So if you take one thing away from all of this, let it be this mental model. Your multi-core CPU is really a small archipelago of independent islands. Each core handles its own business, its own state, its own interrupts. The operating system's scheduler is like the air traffic controller, coordinating between all these islands to make sure all the work gets done as efficiently as possible.
And this whole invisible process, from interrupt to switch and back again, happens in just microseconds. It happens billions and billions of times a day, on your phone, on your computer, creating that perfect, seamless illusion that everything is happening at once. It's a high-speed ballet of hardware and software working in perfect harmony. And it really makes you wonder, right? What other incredible high-speed ballets are happening right now, just under our fingertips?